This week we very good. Okay. So this week we are very lucky to have a high energy seminar, because we haven't had a high energy seminar for the past few weeks. To have pizza and have so many people and so many young students as well. And most of all, we are very happy to have Ilaria Marini from ESO, who is visiting us this week. Okay, we have to click on this, right? So Ilaria is a postdoctoral researcher at the European Southern Observatory, or ESO, in near Munich, in Germany. And she's working there in the CLEVER group. Very funny acronym. I hope you will explain that to us, on the thermal properties of galaxy groups that are observed by eROSITA. And her research interest is focusing on galaxy groups and clusters in X-rays and optical wavelengths, and their role in the large-scale structure. And she has a special expertise on post-processing state-of-the-art cosmological hydrogen simulations, such as magneticum and elasticity ENG. And I think in this talk, she will tell us all the secrets about the universe and clusters and simulations as well. Okay, go ahead.
Thank you. All right. So thanks everyone for being here. I know pizza was definitely one major factor in your choice to be here, but I'm also very happy to see your faces. I'll be talking, as Ako has introduced already, about galaxy groups and the work that we've been doing so far with the group that I have here. There's actually more people than the ones I'm posting, but let's say this is the usual people that I talk to on a daily basis. So let me start, let's say, to introduce the topic with say something a little bit general. So galaxy groups are, let's say, an important element in the large-scale structure. So the universe we know is not just a homogeneous distribution of matter, but we have different structure that composes. So we have nodes, we have filaments, voids, and on top of these nodes, we generally have galaxy clusters, but not only, we also have galaxy groups, which are slightly smaller scales. And overall, the matter distributes in this hierarchical structure. Now, generally, in the lambda CDM model, we expect dark matter to be the largest component of matter, but we also have other components, and most importantly, we have baryons that are part of this picture here. And baryons, even though they represent quite a small percentage of the matter, they are actually extremely important in changing the evolution of matter in the universe. So the main driver of structure formation is gravitational collapse. But once you start introducing baryons are not just affected by gravitational collapse. You also have other astrophysical phenomena happening. So you have pressure, you have viscosity, you have turbulence. In general, you have cooling, which leads to star formation. And all of these events are somewhat the accelerator in the gravitational collapse. So it's interesting to study the effect of baryons because it will tell you how they affect actually structure formation in general. So in this idea then, if you were, for example, to only take into account dark matter, so gravitational collapse, people started doing their calculation and started realizing that if gravitational collapse was the only force in place in the structure formation, then you would have a model called self-similar model, where basically like a Russian doll, structures will form hierarchically, so smaller structures will combine and form larger and larger objects, like a Russian doll. And so basically with this, they could predict what were several of the properties that you would get in this scenario. So in this plot here, for example, I'm showing you the prediction of the X-ray luminosity for galaxy clusters and galaxy groups in general as a function of their halo mass in the scenario where we only had a self-similar model. But then we start populating this diagram with actual observations of what the universe is showing us for these objects. And you see that actually observations are populating quite different part of the diagram. So this is exactly the effect of baryons, just changing actually the underlying physics. And to be interested in galaxy groups would be to be interested actually where most of the self-similar difference happening. So between 10 to the 13 and 10 to the 14. And so actually being able to populate this kind of scaling relations with galaxy groups would actually help us understand how much baryons affect structure formation. So let's say that this is the main reasoning why one should be interested in understanding these scaling relations with galaxy clusters and galaxy groups especially. Now, big problem though, is that we are not quite understanding how galaxy groups work. Now, what do I say this? When we start model galaxy groups in general, and I mean by using cosmological simulations or in general hydrodynamical simulations, we quite understand galaxy clusters. So we are able to reproduce properties of the galaxy clusters quite well. So you see, for example, to the right, you have 4 different simulations with different physics involved. And generally, the gas density distribution on the top panel or the gas temperature in the bottom panel tells you that galaxy clusters are generally quite well understood. Now, if you take these same simulations and you look at the galaxy group properties, you see that predictions are quite different. Now, you have certain simulations, for example, the non-radiative, where of course you don't have cooling, so for sure you are excluding a very important element. But Illustris and Illustris TNG, for example, are 2 commonly used simulations. And what I'm telling you is that one simulation predicts to have almost 0 gas in their halos at the galaxy group scales, and Illustris TNG, on the other hand, is completely on the opposite side. So the problem is that the kind of physics that we introduce it can be quite strong for galaxy group scales. So if you, for example, this is the result of AGN feedback. So if you have a supermassive black hole at the center of your galaxy group, what happens is that the gravitational binding energy of galaxy groups is so shallow that the effect that the AGN can have is to push out that gas away or to eat up that gas, will then eventually might lead to completely depleted galaxy groups or completely filled up galaxy groups. So we don't know in our predictions where we are right now. We want to test this, and that's part of the work that we've been doing. We want to try and understand how we can tell our simulators what kind of galaxy groups we observe in the universe and what kind of predictions we should expect. Unfortunately, the task is a bit hard, and let me explain you why. So obviously, to do this kind of exercise, you want to have large surveys. So you want to have large samples of galaxy groups, and you want to do that in X-rays or in ST. You want to really be able to probe that gas in the galaxy groups. Now, if you look at what you should expect of cosmological volume when you do a survey, you have Millennium XXL, which is the lambda CDM prediction for the amount of halos that you should expect in that volume as a function of halo mass. You have Gamma, which is an optical spectroscopic survey, where you basically are probing most. As you can tell, you're basically following the Millennium prediction of the amount of halos in that volume. And then you have EFEDS, and EFEDS is a very small patch of the sky. It's probably what we'll ever get as the longest exposure for ear zeta data. And you see there what are the number of objects that have been detected with ear zeta. So galaxy clusters are completely there, fully there. But then the galaxy group scale, which is the scale that we're interested in, is very shallow, and we're really missing most of the population. So that's clearly an observational bias that we need to overcome. And one way to overcome this is to, I'm going to skip this. One way to overcome this is by doing stacking. Now, what do I mean? I mean that we have a sample in the optical catalog where we are able to probe these galaxy groups. We're able to find them, and we are able to assign to them a mass with a relative uncertainty, and I'll be talking about that as well. But then what you do is you take the ear zeta data, which is very useful in this case because it covers the entire sky, or in our case, half of the sky. And then you can basically select your region in the sky and then start stacking in different halo mass bins. So from something like this, where you have almost 0 photons in the image, you can then start having actually a signal for your galaxy group mass spin. And so you can do interesting things like getting a spectrum, getting a luminosity, and really just try to understand a little bit the average property of that mass spin. Okay, now, as you saw in the first, before I started the video, that image is basically empty. So what I'm basically telling you is that we have to convince ourselves that when we are stacking stuff that we don't see, we're actually doing something, taking into account as much systematics as we can. And so that's obviously very complicated, and it calls for a dual approach. So you can't just take the data and you can't just stack everything and hope for the best. But you should be able to constrain as much as you can the systematics. And we try to do this by a forward modeling where we approach the problem with the observations, and at the same time we approach the problem with the simulations, where we created fully end-to-end mock catalogs of Zeta and the spectroscopic optical survey that we used. We did the stacking, we understood where most of the systematics are, and so we were really trying to contain as much as we could systematics there. Okay, so I mostly worked on the simulations. In fact, I constructed all the mock for this. So I'll be mostly focusing on the simulation side, and I'll be showing some of the observational results. But if you have questions on the observations, please ask me as much as you want. Okay, so as I said, we need to create a mock observations of this kind of data. So we were interested in the local universe because generally that's the easiest thing that you can observe, especially with galaxy groups. And so what we needed to do was we needed to create a light gun, and we created a light gun with a cosmological aerodynamical simulation called Magneticum. Now, you might be familiar with Magneticum, or might not. Generally, people are more familiar with simulations like Illustrious TNG, but the idea is essentially the same. You basically have a model that follows the dark matter, then you have a model that follows the hydrodynamical particles, so meaning gas, then you have star formation, you have AGN feedback, you have cooling, all sorts of physics that generally are included in hydrodynamical simulations. And then the one in particular, Magneticum, we decided to use this one because against other simulations, it seemed to be the one that best reproduced gas properties of clusters and galaxy groups. Maybe I have a slide I can show you later. So the idea is we create this light gun from an original simulation, and then from within this light cone, we select all the particles or all the objects that emit in X-ray. And that would be gas, that would be black holes or AGNs, and that would be X-ray binaries. Then on top of this, and for each of these objects, we create a spectrum, a theoretical spectrum. And on top of this, we then add a background. So whatever undetected AGN at high redshift that we wouldn't be able to model in such a local universe. Light cone, we then included so that would be the effects background there, the modeling. On top of this, you need to introduce projection effects. You need to introduce distortion given by the redshift. And then on top of this is very all theoretical. You still need to model what Zeta would actually observe. So what you need to do is you need to take a simulator like 60 in our case, and you basically have to introduce the PSF that Zeta would use, the scanning strategy that Zeta would use, the exposure time. So at the end of the day, you can effectively have something that would look like Zeta. So here's one example of the kind of data that we have. You see on the left, that's a real patch of the sky coming from Zeta. And on the right, you have our own simulation. So we were really hopefully trying to get points of the, let's say, the background, the cosmic background underneath, and point and extended sources in our simulation. On top of this, then what we did was we took the Zeta halo finder, we ran it on our mock light gun, and then we tried to see how many galaxy group and clusters we were able to detect, how many point sources. And so at the end of the day, we were able to basically compare an eROSITA mock catalog with the input galaxy group and galaxy cluster catalog that's actually within our LightCon. And so by doing this, you can, for example, recover the selection function of eROSITA with that given exposure. And so that would be what you see on the right here, where you see as a function of halo mass, how many objects are we actually able to detect with this was ERAS4 in eROSITA. Don't mind the different curves. They are just a different likelihood of how likely that object is a true detection, whether it's not, because even if you take different likelihoods, what you see is more or less the same message. You're able to really detect the galaxy clusters, and then the galaxy groups are completely lost. So our mock observation is telling us exactly what the observation is telling us. We're able to detect galaxy clusters. We're not able to see galaxy groups. So having done this, we then need to take an optical mock observation. And that's exactly what we did. We created a galaxy catalog where we added some errors to our mass estimates, to our magnitudes, and so on. This was within errors that state-of-the-art spectrograph would observe, like gamma or even SDSS. And we did exactly the same game where we have this galaxy catalog, and then we pass this catalog to some halo finders to try to see how was the selection function for these surveys. So we did this. We asked actually people that compiled the SDSS catalog and the gamma catalog. We gave them blindly the galaxy catalog and told them, retrieve for us the galaxy groups. So there was no, let's say, bias involved there. And you see that the selection function, again, as a function of halo mass, is telling us exactly what it showed us before, where galaxy clusters are being recovered. And then as you go to the galaxy group scales, the galaxy group scale are still there. Obviously, you're missing some of them, but you are still able to detect them. Now, the difference between the two curves, you have a solid curve that represents if you are able to detect an object, but the dashed line is not only you're able to detect that object, but that object is cross-matched with an input halo, whose galaxy members are at least for 50% the same. So I'm basically interested in not just I'm detecting a halo, but what is the purity of the galaxy member in that halo. And you see that overall, we're still good around 80% for the galaxy groups. So let's say that we can trust spectroscopic catalogs to give us optical positions for these galaxy groups. One issue, though, that we found for the optical was that the purity wasn't as good as the X-ray. And let me give you an example here. So these group finders, generally what they do is they, from the galaxy member, they are able to recover the halo mass of the group or the cluster that they belong to. And most likely what they do is they take the galaxy member, they measure the velocity dispersion, and then from there they extract a dynamical mass. The problem with doing that is that if you get some members wrongly assigned to a galaxy cluster, a galaxy group, you're biasing a lot your measurement of halo mass. And that's exactly what is showing you in the first panel there. So this is the halo mass that the catalog would give you on the y-axis, and on the x-axis, you have the actual halo mass coming from the simulation. So the group finder has a standard deviation of 0.35 index, which is basically telling you that most of the time we are not getting the halo mass for these groups. Now, is there a way to improve this? Well, yes. So we use the simulation. We try to see whether we could somehow improve this measurement of the halo mass. And one thing that we noticed was that these group finder are really good at detecting the most massive or the brightest galaxies in a galaxy cluster group, and they're not so good with the smaller objects. So if we even get the largest and the most massive objects correctly, then we are able to, through a scaling relation, to get the halo mass. So for example, using the total stellar mass or the stellar mass of the BCG or in the end, the stellar luminosity, we were able to get much better constraints on the halo mass. So that, for example, is one way in which we improved our systematics in the sample. And that's really important because we are stacking on halo mass. And so, for example, Victoria Topton, she's a student in our group, she stacked in the halo mass spin, and she recovered the spectrum of each halo mass spin, and then she was able to fit this relation with the multi-temperature relation, and then to finally get scaling relations such as mass versus temperature, which is similar to the very early scaling relation that I showed you, and compare this with the self-similar prediction. So now you see that the error is still quite important there. This is ERAS-1 data, so the very shallow ERA-zeta data. Hopefully soon we'll be able to do this with ERAS-4. But this is generally the idea, to do this kind of exercise both with the observation and the simulation, and then correct along the way whatever we can improve in our mock, and then apply the same thing in the observation. Okay, so a couple of more observational results. We got the hot gas fraction in these halos as a function of halo mass. This is extremely important for people that are interested in understanding the amount of baryons as a function of halo mass. You might have seen a lot this in conferences, and you can see that they were really trying to push here the boundary of where the halo mass is ending. Okay. Let me conclude with something very useful that we can do with simulation, because this is all great. So we can model this and we can understand maybe better systematics in observations. But another thing that we can do with simulations is to try and understand why objects at the same halo mass would have such different quantities of gas. So if you, for example, look at if you, for example, looked at the luminosity versus mass relation for these objects in the light cone, you see that as fixed halo mass, you have quite large scatter in your scaling relation. So what it's telling you is that a fixed halo mass, you should expect your object to contain much more or much less hot gas that's emitting in X-ray. And that's obviously a problem. So what we do is we try to understand this selection effect with our simulation. So we basically traced back each of these groups in our light cone, and we understand why objects that are today very bright are bright, and why objects that are today faint are faint. So basically what this means is you concentrate in one halo mass spin and you test the scatter that you have in this relation. So generally people say that this effect is due to AGN feedback. So the central black hole that you have at the center, what it does, it's fed by gas. And then this gas is then triggering some activity, and that will either push out that gas or will eat up that gas, and that basically that evolution will lead that gas out of the halo. And indeed, we found that this is true also in our simulations. So if you, for example, look at the instantaneous activity of the black hole, what we find is that objects that are generally bright are also objects that are have a lot of AGN activity in that moment. Now, what this means is basically that there's a lot of gas inside these objects, and that the AGN is responding to that. On the other hand, at that redshift 0, these objects have very low AGN activity. So the faint objects have very low AGN activity, which could be a bit counterintuitive. You would expect maybe, they should have more, but actually they don't have any more gas to feed that black hole, and those respond. But if you look, for example, at the black hole mass, so this should tell you how much across time the black hole has been fed, and so has basically had a lot of AGN activity in the past. And you see that faint objects have, in general, much higher black hole masses. So it's basically telling you this. It's basically the faint objects are objects that have had a lot of AGN activity in the past, and they've stopped today. So the question is, that's great, but why, again, would you have this difference in the history of the black hole at the center? Why should you have objects at the same mass that have differences in the center? So we looked at samples of the object. We selected bright and faint, as I said before, in a given halo mass. We went back in time, And what we found is that actually at early times, their AGN feedback activity was very similar. And then as you go towards redshift 0, something happens between redshift 1 and 1.5, where the AGN activity changes quite drastically. So bright samples tend to have a lot of AGN activity, which means that they have at that time a lot of gas, whereas faint ones just tend to go down. Why? And then if you look again at the quantity of gas, and then you start seeing that faint objects just generally tend to have less and less gas, whereas bright objects at some point happen to have a lot of gas reservoir in them. So this we discovered was connected to the mass assembly history of these objects. So objects that today have the same exact halo mass, so at redshift 0, you see that they coincide. You look back in time, and then you see that faint objects just had way much more mass. So around redshift 3, 3.5, these objects were extremely massive. Whereas on the other hand, bright objects today, they were much less massive. There's 1 dex difference in the halo mass. And you see that around redshift 1, 1.5, they had a lot of mergers, which basically gave them the gas that today we observe, and that basically was able to allow for that brightness in X-ray. So possibly, if we give enough time to the bright sample, they probably start depleting once again with AGN feedback that today is active. Okay, this will show you quick sketch of what I meant in case you got a bit lost with my description. So what you should expect is if you observe a galaxy group today and it's faint, your object was probably very large early in time, and then it was never got the chance to be inserted gas again or accreted mass. And so what it did, it just continued its evolution, and that evolution meant that it was basically getting depleted in gas. Bright objects today, instead, they had mass accretion quite recently, and so they are depleting slowly their gas content, but they haven't quite got there yet, and they will probably eventually get there if you give them enough time. Okay, so how can we test this? And that's my last point. How can we test this? So to test this, well, obviously we can't play reverse in our universe and observe whether these objects have accreted later or not. But what we can do is we can look at their dark matter density profile by, for example, using gravitational lensing or by using the orbits of the galaxy members in these galaxy groups. And we can recover the concentration of that dark matter density profile. Why do we want to do that? Because objects that have had a very slow evolution. So the faint objects will basically have had enough time for their gravitational potential to go quite deep, so to be in the scenario above there, and basically to just have a quite deep and quite high concentration in the dark matter density. Objects that, on the other hand, have accreted late in time, so they're bright today, they will have a quite different concentration parameters. So if we can test this, we are able to do that. So simulations tell us that this should be the kind of signal that would actually be confirming this scenario. So you see that there's a quite clearly correlation between the amount of gas that you have in a halo and the concentration. And because concentration is dependent on halo mass, we needed to take into account that. So that's what you see in the different lines. But the trend is very clear. So we really should start thinking about brightness in X-ray as a way of understanding a little bit assembly history and possibly assembly bias. I don't have time to tell you about this, but you can ask me if you want, but there is a connection with the large scale structure. So why these objects should assemble later on. So we are currently testing that hypothesis, but let me just take to the conclusions. So the conclusions here are that we want to understand galaxy groups, and we want to use large samples to do that. And optical selection seems a way to do that. There are many problems there, for example, halo mass, but if you can control those, you can do something like that. And then the hot gas content seems to be connected to assembly history. So maybe there's assembly bias there that can be exploited. And so there's a lot more that we can look into the data and really try to use simulations as a way to find observables to test these kind of predictions. So with this, I think I've gone way over time. So thank you very much.
Thank you so much. Thank you so much. So do we have any questions? Here. Oh,
Thank you for this nice presentation. I was wondering how in Erosita you can separate the AGN and the contribution from the hot gas
Mhm.
to the stack.
Mhm.
Because the luminosity which you see are
Yeah.
the luminosities of AGN.
Yeah. So AGNs, so we test the selection function for the AGN in Erosita, and generally all the, at least in the local universe, all the AGNs that are in the Erosita catalog, in the point source catalog, are generally the AGNs that are present there. So we don't miss, let's say, AGN in the local universe. And so what we did when we started was we excluded point sources that were outside R500 in our sample. And we completely excluded objects that had a point source within R500. So if we couldn't mask it, we just excluded the image there. And so that's how we accounted for that.
Can I ask a quick follow-up question on that?
Yeah.
So I'm not sure, do you introduce any sort of bias by excluding all galaxy groups which have an AGN?
We tested this with the mock, right? We did this, there's no bias. There's an slightly increase in the uncertainty of the scaling relation, but there's no shift, no bias effect in there. So yeah, we're not worried about that.
I see. Hi, the ratio of cold to hot gas varies a lot in Greece. In your simulations, how do you handle the transformation between cold and hot gas?
We decided, for one thing, our cold gas doesn't get any colder than 10 to the 4 Kelvin.
Right, but that's
So-
heated through.
Yeah,
shock.
yeah. So, but that's, I think sometimes people expect actual cold gas, and we don't have that. What we define as hot gas is anything that's above 10 to the 5 Kelvin. And once again, there, what we did is by using this definition, then we checked for galaxy clusters whether the scaling relations there were actually reproducing what we expected them to be. Also, in terms of using this component, when we did all the modeling of the X-ray emission, basically we tested what it means to have particles that have 10 to the 4 or 10 to the 5 Kelvin there emitting, and what it means when you don't have them. So all of that we were able to test, and we discovered that at the end of the day, our cut was stable enough.
I wanted to say, I enjoyed your presentation. I also wanted to ask, what was your favorite part of doing this research?
Say again, sorry?
What was your favorite part of doing this research or the research project?
What's my favorite part? Ooh. I guess finding the answer. No, I think honestly, I think what I enjoy about what I do is that before doing this postdoc, I was in a group of simulators. And so they were very interested in tuning 1 or 2 parameters, whereas now I am the only simulator in our observer group. And so my day-to-day basis is actually understanding what people observe and actually getting from my meaningful prediction something that they can use. So for me, understanding this part, the F-gas concentration, and actually give it to observers and say, do this for me, let's see if this works. That was, let's say, creating a bridge between 2 communities. So that was my favorite part, I would say.
Really also work. You mentioned you have been looking into how the location of the group relative to the cosmic web.
Yeah.
Could you say somewhere?
Yes, thanks. Thanks for the question. Yes, so basically, we were starting to understand, and we're still right now looking into this, and it's very, very complicated, unfortunately. But we were basically trying to understand why an object should start increasing so much their mass, whether there's a connection with the environment. And we found that, so if we looked at the density contrast, so how much matter you have in a given sphere around your object, we started finding that this is the cumulative density distribution of that. We started finding the bright objects tend to be in much denser environments. We have other panels with larger and larger radii, so this is true, and 2 megaparsec, it might be small, but this is group, so actually this is 5 times 500, just to give you an idea of the large scale. But we found that bright sample today seem to be in much more dense environment than objects that are faint. So which means that what we're trying right now to do is basically we're trying to use algorithm like Disperse to reconstruct the large scale structure. And we're trying to see whether we can get this kind of signal also in the real data, because basically Disperse would tell us whether an environment is overdense, whether an object lives in a filament or so on. And so that's exactly what we're doing, but that seems to be highly connected to where this object is.
Hi, I had a quick question on something on slide 9. So
Oh.
it was, I think, about stacking the images to increase the signal. So say like the upper limit on how many images you should stack to get the best signal, or is it to a point where if you overstack it, you might get maybe oversaturation somehow?
So we don't have too many galaxy groups, so maybe we never reached that limit. I personally did not stack, so maybe that's a detail that I might have missed. But stacking technically should work in a way where that signal shouldn't be flushed out the more you stack. But actually stacking should work that the more you add images and that more the background should go down and your actual signal should go up. But maybe I wonder whether there's a limit where you actually go asymptotically. And that I don't know. Maybe I can get back to you with that. I can ask the person.
What happens is that if you add galaxy groups that have higher redshift, so they are more and more distant, then at some point you don't really get more signal from the galaxy groups themselves, but you just collect more and more backgrounds. So there's a redshift sweet spot for stacking galaxy groups, clusters, galaxies, whatever. It's a different redshift, different instrument.
Yeah.
But you shouldn't go to the endless, high redshift universe when you stack something like that.
Thank you.
Okay, I see no more questions. So thanks,
Thank you.
Ilaria and everybody for the participation. Yeah, we'll be here on Friday as well, because there's a lot of time slots open for Friday, and also some I think for today.